Assalamu alaikum, dear students. Bismillah ar-Rahman ar-Rahim. This is the first class of zener diode, and in this slide, I will be just covering around 20 to 21 or 22 slides out of these 31 slides. So, we already have conducted a class, conventional class about the zener diode, but maybe some points from this presentation were not discussed. So, I will be just discussing it here. And in the starting slides I will be just going fast because we already have done a good deal of discussions about the Zener diode, the basic working, and then we will just focusing on the numerical. So uh, you know what is this Zener diode? Zener diode is a p-n junction, and this is the characteristic curve of the Zener diode. In the forward region, the Zener diode just works like a normal typical diode, rectifier diode kind of thing. Or but in the reverse region, this is basically operated in the reverse region. That is the breakdown region. So this is the VZ voltage, and then there are some particular points in this VI characteristic curve that needs to be discussed. So that I'll be just discussing in a bit detail. So what are those points? You see, the main point is that this IZK is the minimum current that a Zener diode should pass through it to make it uh, uh, to make it regulate the voltages. So without passing this minimum current, if you just decrease the current from IZK in somewhere here less than the IZK, then this diode is definitely very visible. That is, it's not in the regulation mode, because whatever voltage you are just increasing here, and it is just appearing on the Zener diode. But once you just pass over this VZ, it becomes a straight line. That means that you just cannot increase the voltage across the Zener diode beyond this range, this VZ. Uh, this is how it works. So the one point was this IZK, the minimum voltage, the minimum current, and this is the IZT, because you see that this voltage is not constant and there is some slope in this VI characteristic of a diode. You see that the voltage is getting higher, slightly higher, as you just increase the current from this zero value to from this zero not zero IZK value to the maximum current. So this Zener voltage VZ is normally mentioned at a some test current, and that test current is in the middle of the whole range of the Zener current. And what is the whole range between that? The whole range is between the IZK, the minimum current, and the maximum current is here IZ maximum. That is not mentioned here. And I just also tell you one more point that Zener diode's data sheet does not have a mention of the maximum current that this Zener diode can handle. Rather, the rating is given in the form of the maximum power that this Zener diode can handle. From this maximum power, we can easily find out the maximum current that this Zener diode can pass through itself. So having said this, I have just emphasized 3 points. That is, this is the IZK, the minimum current, IZT, the typical current, and the test current, and the IZ maximum, which comes out from the maximum power rating of the Zener diode. Right. Moving further, uh, why is this increase in the current, increase in the voltage of the Zener voltages? Because of this RZ. So how do we model RZ? We model RZ in the form of, I just forward, this is the ZZ. Sometimes it is called RZ, sometimes it is called ZZ. In the case of the Zener diode, we normally refer it to this value of this resistance is ZZ. So this is how we just model the Zener diode. Voltage source, that means that this is the Zener voltage and this is the ideal diode, and the non-ideal behavior has been lumped together in the form of this series resistance ZZ. And due to this resistance, what will happen with increasing currents? You see where is the increase? The current is increasing downwards. On the y-axis, the current is increasing in this direction. When you will just increase the current, the voltage will also increase from this point to this point. I hope that this is already clear to you, but even then, you just go through the videos and just focus on the points being discussed here, so that the concepts get firm in your mind, and you will be feeling much easier if your concepts are clear while you are doing the numericals. And numericals need a bit of thinking and focusing. So this was the RZ I just said, and the slope is 1 upon RZ. Okay, and uh, I will be just discussing that's delta I and then delta V also. So as you increase the current from delta I, from test current to the maximum current, this maximum current or whatever current greater than IZT, you will be experiencing a delta V, an increase in the voltage, and that increasing voltage is just due to resistance. So it will be easy to calculate, and I will just doing it in the form of these presentations. So if we just want to find out the value of a Zener diode practically, we can very easily do it. We will just increase the current from delta some value of IZ to a value uh, which increases by delta IZ from this point to this point. So thus we will getting delta Vz here, and from Ohm's law we will be easily find out delta Vz upon delta Iz. That will just give you the value of this Iz. Having said this, we just want to I just had emphasized one point last time. Okay, this Izm is found out with the help of power rating. You see, this is the power rating PD. The Zener diode is of this much power, and you divide it by Vz. So for example, it is 2 watt zener, then and it's a 5.1 volt zener, 2 watt, and 1.5 5.1 volts. So it will be 2 divided by 5.1 volt, and that's how you will be just coming up with IZM, the maximum current that zener can handle. So moving on, ZZ or RZ is same as it is mentioned here. So if you just want to read these points from this PowerPoint slide, this PDF file, you can easily pause the video and just go through the points here, or you can just open a PDF file from your own location. Like this is the PDF file, that is the sixth PDF file, the sixth one. You see, this is sixth file. So I will be just sharing it on your EDC group, the Xenodiode file. So you can just keep it open in parallel with while you are watching this video lecture. So I just don't want to just make it lengthy. So I just skip over it. These are the points. So you see what happens here. A Zener diode exhibits a certain change in Vz for a certain change in Iz. For delta Iz, it is exhibiting a change of voltage by delta Vz. All right, so this was it. So how much was the current change? The current change was from 10 ampere to 15 ampere, and voltage change was 50 millivolts. So 50 millivolt divided by 5 ampere. So where I am just getting these values I am getting from the picture. 10 to 5, 15, that is 55 milliamperes here, and this voltage of is delta Vz as mentioned, it is 50 millivolts. So we come up that ZZ is given by 10 ohms. In the same way, this is a diode and its data sheet is mentioned here. Yes, this is how much power is this? The Zener diode is all the series of these diodes. There are a number of diodes and they all are 1 watt diodes. So they have just written it separately, applying to all the diodes here. So it is a 1 watt diode, and this number is this, and this number is IN4736. It's a 6.8 VZ Zener diode, and a typical value test current is 37 milliamperes, and ZZ, the RZ value, the series resistance is 3.5 ohms, and minimum current that you should pass through this is IZK. That is 1 ampere, 1 milliampere. So that's how from this data sheet you just solve this problem, and just you have to find out the values. Okay. So 3.4 is you just go through it, pause the video, and just read it. All these things. Again, this is one more diode here. Okay. For IZ, where is the numerical? The numerical is up here. Where is the numerical? Oh, this is the numerical. Okay. So we have already just covered it. Okay. So just let me just cover it a bit detail. There is no harm in just discussing the extra things. What happens is, what happens, the IZ, the typical current is 37 milliamperes. The ZZ is 3.5 ohms. The diagonal number is this. So 37 ampere is the test current, and the zener is being made to operate at 50 milliampere and 25 milliampere, right? 50 ampere and 25 milliampere, and the test value is 37. So in this context, if you just see that how much current is changed when the diode is operated in 50 milliampere. So 50 milliampere minus 37, it will have a increase of uh, 30 milliamperes. So 30 milliamperes multiplied by the ZZ value 3.5, it will come out 45.5. So Xenon was 68 volt, and it is experienced a 45.5 millivolt change. So it becomes addition of both 6.85. Okay. Okay, for IZ, when the Zener diode is being operated at 25 milliampere, that is uh, a lesser current, by lesser by 12 milliampere. So it will have a decrease in voltage, and if you multiply this 12 milliampere with 3.5, the ZZ value, it will come out to be 42 milliamperes, and you will just subtract this 42 milliamperes from 6.8 volts. So it will become a bit lesser, 42 millivolts lesser than the 6.8 volt. So it is showing you that you increase the voltage, but the output voltage does not change. And this diagram shows you that you decrease the voltage, but the output voltage does not change. Why the Zener diode will not change with this condition? That that is IZ remains between IZK and the IZ maximum, and this also holds true for this scenario of decreasing voltages. The input voltage is decreasing through the power supply, and the Zener voltage is not decreasing. That is the point which has been just presented here in these two diagrams, right? So this is something a Zener and shunt regulator. We had done it yesterday in the class, and we will also have some more class on Zener diode tomorrow also, and we will be covering it in detail. So I just ended this video right now here. Shunt means the voltage is taken across the zener, and this value of the 7 ohms is the internal value of the zener diode. So the voltage output will be available on these 2 points, ground and this point, this point. Okay, I just added so that I don't just want to make it to a level where you find it difficult to watch in one sitting. Okay, so here I stop share, and then I just stop recording.